Okay.
So I have started. Okay.
Okay.
Let me share back. So, okay. So we are talking about trees, and in trees, particularly today, we are talking about
DF.
the DFS part of it. We are talking about trees, we are talking about DFS, and in that DFS, we are talking about top-down DFS today, not the bottom-up. So we are talking top-down. So for that, we have written a tree here where we are going to a boundary part. Okay. And how to do this boundary part, that is what we are looking here. So that's the reason we are writing a definition. So this is our DFS function which we are writing, which will always take a root. So whenever we get a tree, we always talk about root. No one can hand over a tree without a root. They cannot hand over 7. They have to hand over 3 to us. Then only we can traverse. So that's what we said here, right? So this is our first base case, which we are looking into it. This is the first base case.
Yeah.
Which we are looking into it, which says if root itself is none, then why to do anything? Just return from there. Okay. And whenever we are writing DFS, we are talking about recursion. We are doing same thing again and again. So that's the reason we are using a helper function. So whatever is the function, we are using a helper function to do that same thing again. Okay. And that is the reason we move to a different tree, and just to see what this tree consists of. So tree consists of a root, which is nothing but the parent. It consists of the leaf, which is the last node, and which it consists of an arbitrary node. Okay, which is a middle node, any middle node. So whenever we write a recursion, we are looking at this a tree sort of thing where this is nothing but the arbitrary worker. Okay, these are the leaf nodes, and this is the arbitrary node. So whenever we are writing any helper function here now, we will be thinking of two things. One is this arbitrary node, okay, and second is any leaf node. That's what we will be thinking now. Okay, so this is what it is, and then we have to think whenever we talk about arbitrary worker, what we have to think is what he inherits from his parent and what he gives to his children. That's what we have to think while writing it here. Okay, for this particular guy.
Yeah.
Okay, that's what we are thinking. So that's the reason we are writing a helper functions. But so first case will be our base case. Something does not works correctly, what should we do? And something works correctly, what should we do? Okay. So in this base case, what can we check? Is basically we can check
if node has children.
If node whatever was passed dot left, okay, is not none, and same thing, right? Node, sorry, this should be small case. Node dot right is not none. Then only we have to do something, right? Something, anything, whatever we tend to do, we have to do it here. Okay.
What about it has left child but not right child?
Yeah. So what is this case? Basically, I said, right, we have to write it two ways. This is one for arbitrary worker and one this is for node level. Okay. So this base case is always leaf level. This base case always talks about leaf level.
Okay, got it. When
Leaf level. Okay. So if we have, so I'm just writing a basic flow of code, just like yesterday, which we can use later on also. Okay. So this is a leaf level. So something whenever we found out leaf, whatever we want to do, we will do it here.
Yeah.
Okay. It might be written or it might be print. It might be do something over here will be written here. Okay. And mostly we will return it from there.
Yeah.
Okay. That goes here. But so here there is a return. So whenever this case is met, we do return from here, not here. It should be. It should be inside that if. Okay. So we return. Okay, we return from here. So this base case has been done. So now we know that we are not working about the leaf node. Now the other thing is the recursive case. So what is recursive case? Recursive case is the case which is actually talking about this arbitrary worker. Okay, what he gets from his parent and what he gives to his children. That's what we are saying, right?
Yeah.
So for now, we are doing nothing. We are just traversing this tree, right? So we are doing nothing apart from just traversing it. Okay,
Yeah.
so that's the reason we had nothing to do it here also whenever we reach a leaf node. And mostly here also we have nothing to do. So what we will do here is basically we will see that if, okay, node dot left is not none. So basically node of dot left present, this present. Okay, what we do, we called dfs underscore helper, okay, and pass this
Node
dot left.
left.
Okay, if node dot right is not none, okay, what we do, we call dfs of helper
Node dot.
and pass node dot right. Okay, so let's only think of this code for now and let's see what we can do on this tree. So let's think what we started here. We started with a root. Okay,
Yeah.
and you remember, right? We used a queue in our BFS code. Okay, but here we are going to use a stack, and that stack is not created by us. Okay, it's a call stack.
Okay.
Okay, it's a call stack. So imagine this is as a stack. Okay, let's see how it comes into play now.
First in,
Whenever,
last out.
yeah, so call stack is first in, last out.
Last out.
F5, F4. Okay, yesterday we did a queue.
First
Now
in,
we are
last
talking
out. FILO.
LO. So this is first in, last out. Okay. Okay, first in, last out. Okay, that's what we're talking. So let's see how it works. So first of all, we are getting this 3 as a root. Root is not none, so we are not returning anything. We are going ahead. Okay, till now we are not called it, but after this, right? So let's see that this is a continuation of that code. Okay, we have to call that DFS helper. DFS underscore helper and pass that root. Okay, that is what we are passing. So this is the last line of code after this. So this is what we are doing. So once it is calling root, so here that tree goes. We see that tree of left is not none. No, it's not none. So we don't lie into this part. We come here in the recursive code. We say that 3 of left is not none. Of course not. It has some value, right? So what we do? We call the DFS again. So the DFS of 3. So let's write DFS of 3. DFS of helper, okay, of 3 goes in a call stack. It has not yet completed.
Okay, it's still
rather
waiting. Okay.
It's still waiting for its answer. Rather we go here and we say DFS
of 7.
DFS of 7, helper of 7, not DFS, helper of 7.
Yeah.
So we do helper of 7. Now helper of 7 does not have anything, correct? So whenever we go ahead of this, DFS of helper come in here, right? It takes 7 here and it comes here. It says it does not have left, it does not have right. What it says, just return. Okay. So this stack, this flow is completed. Okay, and it returns back to 3. The control goes back to this one, correct? So 3 left somewhere here, right?
Yeah.
3 left here. We left 3 here, correct? There, this is where the 3 stopped. So we go ahead and it says node dot right is not right. So 3 does not have ending. It's still 9 is there. So we pass 9 into it. Okay. So a new stack is created of DFS of h of 9. 9 goes in, it says, okay, it's not reached the leaf,
Mm-hmm.
goes in the recursive node. Okay, it says it has a left. So we call
DFS of 15.
DFS of H of 15.
15.
Okay, so now it is going into 15.
Mm-hmm.
Okay, so it says, okay, 15 is a leaf node. I am a leaf.
Yeah.
I don't have anything, so I will just return. So it says, okay, my job is done. Okay, I'll return to him. He says, okay, I left it here. I'll move ahead. Now it is a part of 20. So I go and take DFS of H of 20. Here, it goes here. It says, okay, I'm a leaf node, return.
Yeah.
Okay, so he also returns. He says, okay, where I came from, I came again from 9. Go back to my 9. So 9 comes here. 9 says, okay, my thing is done. I got my answers. If there was any answer here given by them, I got my answers. Right now, the answer they gave is that we exist and we return to you.
Yeah.
Okay, so he says, okay, I got my answer, so my job is done.
Yeah.
Go back to my 3. 3 says, okay, now my write is also done, my job is also done. So call stack is empty. And we terminate the program.
Yeah.
Okay, now why I told you this is because if you remember clearly yesterday, we were talking about 3 things, right? We were talking about 3 things to do traversal. One is if we have a spike on everything and on its left, we can touch this node when we are just touching its left part.
Yeah.
Each node, right? That is one thing. Then if we had a spike on this nodes on its bottom, we can touch this nodes when we are traveling it from its bottom. And what if it has a spike? Let's take that. What if it has a spike on its right side? We can touch all these nodes, okay, while going from its right side. Correct?
Yeah.
So that gives you the first one, red one. What red one gives you is, what is red one?
3.
So its parent is first, then left, then right. Correct?
Yeah.
Parent first, left, and right. So what is that? So red is giving you pre-order.
Yeah, pre-order.
Okay, let's see how we can do this pre-order in this code.
Okay.
Okay, so pre-order, first print, then go to its left and right. Okay, so if we just write a print here, node dot value, it will be a pre-order.
Okay. Yeah.
Okay, now what is the blue part doing?
In order.
Yeah, blue part is in order.
Root comes in, parent comes in between.
Yeah, so first left comes, then parent, then right comes.
Right. Yeah.
So if we print the value of that node when we are traversing here,
it is in order. Okay.
it is an in order. Okay, now the last part. I will use a different color even though that is post order. Post order, right? So whenever we print afterwards, we have done with our print node dot val. Okay, that is our post order.
So post order is left, right, and root, right?
Yeah. So let's write that also. So this is root, left, and right.
Okay. Yeah.
I'll use root, okay,
Yeah.
left and right. Okay, now this is the second one. How it is?
Left,
root, right. And the third one is what?
Left,
right,
root,
and root. Okay, so if we do any, so in our code we won't use all the 3 at one time, but one of this will be using. Either will use this, either we use this, or this, right?
This. Yeah.
Gives us traversal.
Mm-hmm.
Okay, that defines our traversal, whatever we do.
Mm.
Okay, so that's
Yeah.
the reason I kept this blank, because we might be doing some things later on in this
Yeah.
one, but not in this particular scenario.
Mm-hmm. Yeah.
Okay, so this is the outer function, this is the inside function. I wrote this function inside. Okay, and then this is also up on this level here. So after this is happening. Okay, you can write in a different way also. Basically, you just write this function and then call this and this
Call this
separately.
one.
Yeah, but that then why I wrote it inside, because if you are using some global variables, right, then you don't need to pass it. But if you write it separately, then you have to pass that global variable, right? A reference to that global variable.
Yeah, yeah.
That's why this is the way it, like, is preferred to be written.
Yeah.
Okay. This again came back like yesterday. One second, let me open it. So anyway, this you got it, right? So now let's go to another one. Okay. So let's now take one example. Okay. And let's try to do something on that.
So this pre-order, all DFS will be recursions only?
Whenever we talk about tree, okay, mostly it's recursion.
Because yesterday we did traversal, right? Sorry,
we
iteration.
did traversal, we did iterative way. Okay. So you'll come to see one more interesting thing when we'll complete this part. Okay. So let's take, so now whatever we did, right, in the previous one, let me see if I can open the old whiteboard here. Okay, so this is what I was talking about, is top-down approach, right?
Yeah.
Why top-down? Because we are first going top-down. We are not going from down to up.
Yeah.
They're going top to down.
Yeah.
Okay, so that is why it is called as top-down. And yesterday also BFS way, we were actually going level to level. Correct? We were going level to level.
Yeah.
So even that is similar to this top-down approach. Okay.
It's similar to top-down. Yeah, because we are coming from one level.
Top to down. Okay.
Top to down, yeah.
So that is also similar approach. So what is the time complexity here? So T of n.
We are touching every node one time, so it should be n nodes.
O of n.
Yeah.
And S of n, space complexity.
Complexity. We're not doing anything, right? Creating a new thing.
We are not taking anything, but there is a call stack which is happening.
Oh, okay.
Which is happening for each node.
So n callbacks.
So O of n. So yesterday also we saw this same complexity in BFS. Today also, yesterday S of n was because of the queue. Okay, because this is a balanced trees, right? Which we are talking about something called as balanced tree. But there can be a tree which can go just like this, right?
Yeah.
It can be a skewed tree. So that time this is n.
Yeah.
That will be taken up by the queue. Correct? Or it can be another way. At one time we are taking only one thing, right? But what if this has 3 nodes inside it?
Yeah.
Correct. So now this is 3. So 1, 2, 3, 4, 5, 6. So total is 6. Okay, but at the end leaf node it is taking 3. Okay, and always remember the complexity of n by 2 of anything is approximately equal to n.
Okay. Yeah.
Okay, it does not matter what comes here, basically. Like half of the way also does not matter. It is as equal to n, as bad as n.
Okay. Yeah.
Okay, or as good as n, whatever is that time approach for that. Okay, so that's why for this also, for BFS also, so this is DFS top down, and this is same thing was working for BFS. P of n was 0 O of n, and S of n was O of n. Because in BFS also, we were going each node once. Even
Yeah.
though whatever while and for we were writing it. But finally, we were touching that node once. We were not going back to it. It was always one. Okay. So
But the space complexity, right? We created a queue.
correct.
We created a temp value. We were like made
Does not matter. So
result and everything.
no, does not matter. So even if we created a result, right? So how the complexities are basically, it's like, so take an example, okay? Take an example of space complexity. S of n, we have O of n and O of C1 plus O of C2, whatever, right?
Yeah.
This does not matter because once this n tends to infinity, right? It goes to infinity, n goes to infinity, the constants are as small as 0. So we exclude this part. That's why we always say worst n complexity. So whatever happens here will not add anything here, because this is the maximum thing which we are using in it. Same way goes for time complexity. There are a lot of things. So even though we are touching it, right? Touching it, but there are a lot of things. Checking this is a constant time. Checking this is a constant time. Calling this function, it is a constant time. But we don't calculate for everything. We are checking this, right? If it is a leaf node, it's a constant time. What matters is the biggest complexity in an equation.
Can you explain the space complexity calculation again? I didn't get that.
This one?
Yeah.
So this is just an example. Okay.
So
We will discuss this again with some example right now. Okay. So there will actually have some, here it is a simplest code, right? We don't have much things into it.
Yeah.
Okay, but there we'll have some more things to it, so we can discuss.
Yeah.
But we'll come to this point.
Sure. Yeah.
So let's close this. You got that, right? So this is the tree and this is how we traverse.
Should we take a screenshot for this?
You have recording now.
Oh yeah, okay.
Okay. Or else I can take screenshots later on. And little bit it has moved, if you see here, right?
Yeah.
It has little bit moved because of my hand gesture.
Oh, okay.
Okay. So anyways, but this is what we have. Okay.
Yeah.
And then let's go back to one of the problem. So we have a problem. Okay. There, what we are doing, this is a path sum problem. It's an easy problem. It says given a binary tree and a sum, determine if the tree has a root. Okay. Tree has a root to its leaf. So we have to find some tree root till leaf, and it should match up with some sum which they are given.
Okay.
Okay, that is what we have to do, and what we have to return. If that is present, we have to just return a Boolean expression.
True or false. Okay.
Okay. So let's draw that tree.
5, 4, 8, 11, 13.
5, 4, 8, 11, 13, 4, 1. So we have 5,
4, 8,
8,
11, 11, 13.
4, 1, and 2 and 7, I believe.
I don't remember that.
Okay, yeah. 2 and 7. And what they are saying is the target sum or sum. They are saying the sum should be 22.
22.
Okay. So if we see, there is only one possible way, but that is present. 5 plus 4, 9, 9 plus 11, 20, 20 plus 2, 22. Okay. But if we go this way around.
So the sum should be all the way till the leaf?
Yes. Till
not just in between. If we find the sum, okay.
This is what we have to find. Okay. So root till leaf, this is the sum we have to find. Okay. So how we can write this? So now we know how to traverse at least.
Yeah.
Okay.
Drop down.
But now we have to find how to write it. Okay. And here the output should be true or false. So it should be true or false. Okay. If you observe carefully, so 8 plus 13 is 21. 5 plus 4 is 9. 9 plus 1 is 10. 10 plus 8 is, okay. There is no other way, but only this way, right? Right now we have the sum.
Okay.
Okay. So let's see.
As soon as we find it for one leaf, we can return true.
We can return true.
Okay.
Okay. So how can we write it?
We have to go until the down.
So first, let's start with our overall solution.
Okay.
Define what we can say main. Okay, main or solution.
Okay.
Solution is our thing. So we are given two things. What we are given is root, and second case is sum. Okay, that is which they have given us. First base case always goes there. Okay, if
Root is none.
Root is none, return. So here return false, right? Because we don't have that sum. So we'll just return false. But what we will do now next, okay, root is not null. We have to have a global variable to store that result, right? Whatever is our result. So we'll take a global variable as a result and initiate it with false. So we are saying right now I'm assuming it is false, but let's see if we have to flip it or not flip it later on. Correct? So that is what we are doing. And then let me see if I can move this somewhere else. Okay, so why I did it, I will come to know. So we are saying to do something if we are done with this, okay? So here is where my helper code will come. Okay, but once my helper code is done, what we have to do is basically we have to call that helper, right? So we'll write a helper function. Okay, so say we are saying DFS function we are writing inside it. Okay, and for that DFS pass what? We have to pass root and we have to pass sum. Okay, and then whatever is our result, return result. Okay, now this code I'm writing it here. Okay, this whole thing I'm writing it here.
Okay.
So what is that helper function? So let's write my DFS code.
Okay.
DFS code. What I'm taking a node. And what I'm taking some target for my node. Okay, so this is my node and there is some target. This is my target. Okay, now how I think to go through it is, this is the parent. Whenever parent says, okay, I'm done with my work, now you do your work. Okay, he's handing over the responsibility for this node to do his work. He's handing over the responsibility for him to do his work. He's handing over the responsibility from him or him to do this work.
Yeah.
Okay, so what I'm saying is, this is my target and this is my value. When I give you a recursion problem, which you will finally hand it over to your child, I will do my job and ask you to do your job.
Yeah.
So what is my job? I will say, for me, the target was 22, but for you, the target is 22 minus 5. Same for my other child. My target is 22 minus 5.
Okay.
Similar way, 4 will go down. He will say, okay, 22 minus 5, how much it is? 17. 17 was my sum, but now for you, it's not 17, it's 17 minus 4. 11 will say, okay, my job is easy. I have 17 minus 4, that is 13. My job is 13. So for me, I have to subtract 11. When it comes to 2, 2 says, okay, my value is 2, I got 2. 2 minus 2 is 0. So finally, the sum and my value are matching. If that is matching, then and I'm a root. Sorry, I'm a leaf, right? Then we have achieved what we want. But here, it won't happen. But we are not going here. Basically, when we are landing here, we are coming here and going here, it is ending. We are even not going here. Okay. Got it? So that's what we are trying to do. So for doing that, the first base case, whatever we write is what? As I said, right, we have to write we have to write two cases.
Yeah, the leaf.
One, what he will do. This is 2. And first one, what he will do. This is 1. Okay. So let's talk what he will do about it. Okay. So how we'll first of all know that we have reached here? Okay. So that's our base case. Sorry.
If it doesn't have left or right child.
So that's our base case, which is of leaf. Okay. What he says is, if my node which has been passed to me dot left is not none, not none, it's is none. Basically, we are now is none.
Yeah.
Is none, and node dot right is none. Okay. When we know that this is there, I have reached my base case. I have reached my leaf. But to stop this flow or to do something over it, to take some action, we have not yet reached that part. Okay. So I'll say after that, if I'm a leaf, but my node dot value is logically equal to the target which was passed to me to finish, to achieve. Okay. If that has been written, then I will mark that result. It's a global variable, right? So it is accessible here. That's the reason this box is nothing but this whole thing. Yeah. Result equal to true. True. And once that happens, I'll just return from here.
Okay.
So we are done with this. So this is nothing but 1. This is nothing but the 1 code.
Yeah.
Now we have to think of what
the
arbitrary node will do.
Yeah.
Okay. So for him, so this is the recursive code. Okay. Of RP node. Okay. Sorry. So I'm writing something for that guy. Okay. So how I will come to know? So here it's much more simpler. If node left is not none, what we have to do?
We have to
call DFS. We have to call that helper, right? Same node, but on what?
Node dot left.
Node dot left. And what we have to do? the target changes, right?
Target minus node dot val.
Node dot val.
Yeah.
Okay. If
Node dot right.
is not null, what I do? I call DFS with node dot right
Target
and minus
node dot
node
val.
dot val.
Yeah.
Right?
Yeah.
So this goes and fits in here. This is that
Yeah.
part.
Mm-hmm.
After that, once we complete that code, we just call that DFS with the root and sum,
Mm-hmm.
and then we return the result. So if there is something, the result must have been flipped.
Yeah.
That's it. And we are returning. So even though, so we are done there itself.
Mm.
Okay. So now here, if we see the time complexity, we are not yet touching n, but the worst case, if this was the part where the sum was getting calculated, worst case,
Mm-hmm.
then the t of n was
Often.
O of n.
Yeah.
Correct. Now what about s of n?
We created one Boolean value
Okay, so
in
that's what
memory.
we will take. Okay, let's talk about that later. First is the stack, right?
Yeah.
Everything in the stack. So that will have worst case. Okay, best case of that will be height of the tree, which is log n.
Yeah.
Okay, but worst case will be O of n if the tree is not balanced or it is skewed on one side.
It's skewed.
So that is O of n.
Okay.
Okay, plus what we took a result, Boolean result. So that is O of 1.
Okay, so it's constant.
It's constant, right? And even if we had some other thing, and if it is not greater than n, we can ignore it, basically.
Yeah.
It is equal to n, we have to consider it. But if it is not equal to n, we have to ignore it. So this basically goes into ignorance.
Yeah.
That's the reason. That is what I was explaining you there.
Yeah.
We didn't add anything. That's the reason we always say it is this.
Yeah, now I get it. Yeah.
Okay.
Yeah.
So this is the complexity of it. Okay.
Yeah.
So this is one thing. Now we have another similar problem. This is one problem done, right? You understood this.
This one I understood.
Have another similar problem, which is a medium problem. Okay. So what they are adding is in this thing 5845. They are adding one more node to it here. Okay. Now you have two ways of getting the output. So this is one way and this is the another way.
Oh, okay. We have to do both.
So we have two things, but now the output they need is
the path
everything. They want the result. So they want it is in 5, 4, 11 and 2. And the another thing he wants is 5, 8, 4 and 5.
The first root is 5, not 3. I thought it was 2.
It was 5, I believe. 5.
Yeah. Okay. Yeah.
Here also it's 5, right? Same thing. Same example, I believe.
Okay. Yeah.
Only 5 has been added. Okay. So now we have two things here. We can write the same code. Nothing changes in this, right?
Yeah.
Because this remains the same. But this changes.
Return will be array. Okay.
So return changes to an array now. So return gets replaced with an array. Empty array.
Yeah.
Result is empty array for now. One more thing changes here is here also we don't do. We'll
just
return an empty array, something like that. But it's better to write a new code for it. But it will follow the same thing. Things will change, will be mostly in the helper. So these are the small changes will happen here, but main things will change here.
Yeah.
Okay. Let's see how we can do that. used it. So let's draw that again. 5, 4, 11.
That is gone.
No, that's there.
Okay.
So now we have two routes, two paths where we have this sum.
Yeah.
This, 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 this.
Yeah.
Okay, that is what we have. So we'll write the same thing again. So simple, right? We'll write define solution, which takes a root and gives us some sum. Okay, it gives us that data. And then what we say,
Best case.
we say if root is none, what to do?
Return empty array.
Return an empty array. Okay. Then some code which will help us to get to this solution. Correct? And then we have to call that code. Okay. But now, while calling that code, what will require? So we'll again call that DFS. We'll pass a node. Okay. We'll pass a sum. And we need to collect results inside it, right?
Yeah.
So results inside it. And then we'll return the final result. Okay. Now this code changes a little bit. So even the signature changes a little bit.
Yeah.
Okay. So let's write.
We never defined result.
Oh, we never define result. Okay. So here result is equal to an empty array.
Yeah.
Okay. So define DFS. In this DFS, we take a node. Okay. We take a sum or a target
And
we want to achieve, and we take a slate. You can take any variable.
Yeah.
I'm calling it a slate. We write it and we rub it. That's the reason slate.
Okay.
Okay. So what is this? So what are these two things?
This is the tree. This is the sum.
So this is nothing but a sub problem. Okay. This is a recursion, right? So this part is nothing but a sub problem for this person.
Yeah.
This guy.
Yeah.
And what is this? This is a partial solution for again this guy. Okay. Any arbitrary node. Just remember this because it will help you to remember what things we have to take. So we have to take a sub problem and we have to take a partial solution. Only two things.
Yeah.
So sub problem consists of node and target, and partial solution consists of a partial solution, that bucket of that solution.
Okay. Yeah.
Okay. So let's write the first test case. So first test case goes always for the arbitrary worker. Oh, sorry, the leaf worker.
Yeah.
All right. So we are talking about a leaf now. We know how to find a leaf, right?
Yeah.
If
node is
left is none and sorry,
node dot right is none.
Is none. right? When we do that, we know that we have reached a lift. Okay, but now we don't know if we have achieved our solution there. That we have to check again. So if
node dot val equal to
target is logical equal to, okay, logical equal to target, we have to do something. Okay, now what is that something?
Return slate.
Okay, so we have to return that slate. Okay, so we'll write result. You have to add it to result, right? Result dot append
that slate.
to that slate. Okay.
Yeah.
But this slate, right, can be a mutable thing. That means it can keep on changing, right?
Yeah.
So if we just add a slate, it might end up having a new value at the end because it can be a referenced value. Okay, so we have to pass a copy of slate. This is the Python way to do it. Okay, this is the Python way. So this is an array, right? I'm just saying, just copy that array and put it into it. But if you want to do it, you have to copy that slate into another temp variable and pass that temp variable here in JavaScript.
Okay. Yeah.
Okay, Python, it's easy. It is saying it is a new thing now.
Okay.
Yeah, so start to end, go start to end, but in a different variable. That's what it said. Okay, slate. But now this slate, okay, if you think correctly, we started with 22 here, right?
Yeah.
We came down, but when we came down here at 2, my slate was not 22. It was 22 minus 2. Because this is what we are checking. We are checking my value is 2 and it is equal to 2.
Yeah.
Correct. So slate has not yet completed its task. Okay. So we have to write that to slate.
Okay.
So that's the reason we say
slate
dot append
value node dot val.
Okay.
Okay. Then we have to copy it to result. Okay.
And that is what we are copying into result. But if we leave that slate here, what we did, slate had 5, 4, 11, 2. Now it will take a turn and go back here.
Yes. So we have to clean
Correct.
it.
We have to clean it.
Yeah.
So
slate equal to empty array.
Pop. Not empty array, just pop.
Yeah,
check. Think of this mode. We have reached 7. We just have to erase 7 and go back to 11 and then add 2. So only pop that last one. Don't pop everything.
Okay.
That's what we are doing here.
Just remove the last. Okay.
Correct. That's what we are doing here. And then return. Okay. So that is my leaf level work is done.
Okay.
Now I'm talking about some middle nodes. That is.
So yeah, one question. That slate.pop, will it execute if node is not equal to target or not equal to target for both the cases?
It will be equal to target, then only it will work.
Okay.
So we are only appending it when it is equal to target, right?
Okay. Yeah. Okay.
Now same thing comes for arbitrary node. What we were doing, if node dot left is not none, right? What we were doing, we were calling this function again. The same thing we were doing. If node dot right is not none.
Yeah.
Okay, we were calling the DFS function. DFS. We are passing node dot left. Node dot right. Then we have to pass the target.
Yeah.
What is that?
Minus node dot val.
Node.val.
Node.val. Now slate. We have to append slate.
So we have to append slate, right?
Hmm.
So let's do that. Okay. What we are appending to slate?
Node.val.
So we are passing slate here, passing slate here. But as we did that, same issue will come if we don't clean it up.
Yeah.
Right? So if we are doing it for this, we have to also do it for this, right? He also can go back.
Yeah,
to 4.
yeah.
He can go back to 3 or 5. And then again 5 has to start fresh.
Yeah.
So okay. Nothing changes in time complexity because it's, I don't know why this keeps on happening.
It's okay.
So nothing changes in time complexity. So T oh good, we are on the same one. So T of n is equal to O of n.
Okay.
Space complexity.
Okay, again O of n.
First of all, we are of course using O of n because we are going through a stack, call stack.
Yeah.
Not a explicit thing, but implicit, but still we are using some space. So call stack, S of n plus we are using slate. How big slate can go?
No, not more than n, right?
Worst case is O of log n, height,
Yeah.
right?
Height, yeah.
If it is a balanced tree, or O of n,
Yeah.
but not more than that.
Yeah.
Correct? And how long can result grow?
Same
It may
time.
not be n, right?
Yeah.
Yeah, it may not be n. It will be less than n.
Yeah.
Okay, so some constant data, O of some constant value, right? But these things are less than
O of n.
O of n. If this tends to infinity, this will be negligible. This will be actually negligible. This depends. If it is not a balanced tree, then n. But if it is a balanced tree, then log n.
Okay.
But still, it will be negligible in front of n.
Okay.
Okay.
So if it's not a balanced tree, it can go up to O of n. That's what you said there.
It will be always, yeah, O of n, right? If it is not a balanced tree, the height will be O of n. That
Okay.
time.
Yeah, slate. Okay.
Okay. So this is our S of n basically.
Yeah.
Okay. So that's all for today. So
okay.
If we see exactly same codes here, okay, and it works.
Yeah. Okay.
Okay. It is an accepted solutions.
Yeah.
Okay.
Okay. Yeah. Sounds
So
good.
that's all for today.
Yeah. Tomorrow it's bottom up.
Yeah. Tomorrow we'll see. the bottom up scenario or the remaining part of trees.
Yeah, sure.
Okay.
Yep.
Chalo, but you are getting this right. So try to do problems because
Then I can get more. Yeah.
correct.
Yeah, I'm doing. Yeah, I'll try to do
Let me
more.
stop recording.